All right, so this is the first lecture to Unit 3. We're on the notes page, page 1, and we're looking at the solution process and electrolytes. The first thing that you want to notice is that there are 3 steps to any solution process. The first step is going to be breaking some sort of attractions. Now notice that the attractions are not bonds. We're not using that word, although in some cases they will in fact be bonds. We want to first break our solute attractions, and then we want to also break our solvent attractions. So these attractions, again, they're not bonds, but they could in fact be something such as intermolecular forces. And so you might see that you have some London forces that might be separating, or it could be hydrogen bonding that might be separating. And then again, in certain cases, you will in fact be breaking ionic attractions, which are also known as electrostatic attractions. The third step is that you're going to want to form new attractions between your solute and your solvent. So depending on how the solute is bonded, which would either be ionic or molecular, that will dictate what kind of attractions are going to be formed to the solvent. And again, depending on how the solvent has its bonds, that will dictate the types of attractions that it can form with the solute. So let's begin just looking at an ionic solute. And for ease this unit, we're going to be having a solvent that is really pretty much just going to be water. And we'll switch our solvents a little bit later on, but for right now, we're going to really want to be sticking with water, okay? So the first thing that you're going to notice is that we want to look at our solvent. Let's just draw out some waters. Here's our oxygens. And then keep in mind that when you're doing these, you want to be thinking about what kinds of attractions they're going to in fact have. So for us, water, you might remember, actually has hydrogen forces, so hydrogen bonds, which means that the hydrogen atoms are attracted to the oxygen atoms on the other water molecules. Those are going to be the attractions that we want to end up breaking as we begin to react. Over on the other side, let's say our solute is ionic, and we're going to go with something simple like sodium chloride. If you remember our ionic compounds, some of the main points about our ionic compounds is that they have positive and they have negative ions. Because they have positive and negative ions, you'll notice that I'm rotating the ions. And so let's make the green ones our chlorine, and we'll make the blue ones our sodium. Now the attractions, because it is ionic, are going to be the ionic bond itself. Oops, there we go. Which again, most of the time we don't use the word bond, so let's call it the other name, which is electrostatic attraction. And electrostatic attraction really just means that you are looking at something that has a positive charge and a negative charge. And because they have positives and negative charges, they're actually just attracted to each other, right? Opposites attract. So in step 1, we're going to separate those attractions, the actual ionic bonds. In step 2, we're going to separate these hydrogen bonds, which again are not actually bonds, but they're instead intermolecular forces. And so a nice attraction between the molecules. Now notice this is an actual molecule, and we know that because both hydrogen and oxygen are nonmetals. So we're looking at a covalent, we're looking at a covalent molecule, which means the water is never going to separate as we look at our solution. We're not going to have water molecules that separate the oxygen from the hydrogen. It's always going to be our water molecules as molecules, where the hydrogens and oxygens are still in fact bonded together. All right, so as we then create our new attractions, again, because the substance is ionic, we're going to end up separating the ions throughout the solution. And as those ions are separating, they're going to need to try to create new attractions that are being formed. So our sodium ion is going to attract to the oxygen, and our chloride ion is going to attract to our hydrogens. There's our chloride, here's our sodium. So again, the sodium is going to attract to the oxygen. Because the sodium is positive, the oxygen will be negative. The chloride, being negative, is going to be attracted to the hydrogens because the hydrogens are positive. And so we make a solution in which the sodium and the chloride ions are separated, and then the water molecules remain intact. Now, if you remember from basic talking about any sort of reaction, see how our water is in fact on both sides of the reaction? That really means that when you write one of these reactions showing the dissolving, you are going to in fact remove those water molecules from either side of the reaction. They don't need to be there, and usually what we do is we just fill in our phases and show that the water molecule was present by using aqueous as our symbols of the ions. Now this is specifically known as a dissociation reaction. It's also known as a dissolving or a solution reaction. And the reason is because you can clearly see the sodium and chloride ions dissolving, but because they are ionic, you can also see them dissociating. They're actually separating away from each other. Okay? That makes sodium chloride an electrolyte. And not only does it make it an electrolyte, but it actually makes it a strong electrolyte. So an electrolyte is any substance, really it's got to be an ionic compound. And there's going to be a few instances where we'll have some covalent compounds, which we'll get to in a little bit later on this unit. But an electrolyte needs to have that dissociation. And so they are called electrolytes because there's a positive and a negative ion that has separated. And so they can then carry an electrical charge. A strong electrolyte means that the compound is actually able to dissociate 100%. And so that means with sodium chloride, it does so readily. All of the sodium ions are going to remove themselves from the chloride ions. On occasion, you're going to encounter a weak electrolyte. And a weak electrolyte is just any compound that will dissociate less than 100%. And so instead of getting that nice full dissociation that we saw up here with our sodium and our chloride ions, you might actually end up with some still remaining down at the bottom. You've seen probably some of those. Those are the things that we sometimes call precipitates, or they just didn't dissolve well. And those are going to be our weak electrolytes. At this point, we're going to consider those weak electrolytes reasonably insoluble. A lot of them will in fact form precipitates, and a lot of them are going to remain a solid at the bottom of the container, and so those are insoluble. So strong electrolytes are going to be highly soluble, and weak electrolytes are going to be insoluble for this unit. You actually have an entire piece of information that is your solubility rules, and they are located in your lab manual. They look like this if you go into your lab manual into the appendices, and you'll see that we have over here we just have the names of each of the groups that we're looking at. What kind of ions are you looking at? We have the ions themselves so that you can see the symbols and the charges. And then again, we have soluble, those are your strong electrolytes. And over on the other side, we have insoluble, those are your weak electrolytes, so that you can start to look at those. For this unit, you're going to want to really use this table to your advantage because it's going to be exceptionally helpful. All right, so let's go back over to our notes. And now we're looking at molecular solutes. And again, we're going to be dissolving those molecular solutes into some water. So our water molecules, they're still the same. And they're, again, still going to be molecules, right, because they're covalent. They're still going to have the attractions of hydrogen bonding. And so when they go into the second step of the dissolving process, they are in fact going to be trying to separate those hydrogen forces. And so let's just draw those again. Again, hydrogen forces, the hydrogen atom needs to be attracted to the oxygen atom. If we then go over to the other side, our molecular solute, if you remember, that means that it's covalent. And that means just like water, because it is covalent, it is not going to be dissociating, although it can in fact dissolve. So let's say that we have a nice solid, and let's say that our solid is iodine, and it has solidified. So notice the difference is that our iodine molecules are close together, they're tightly packed, they're well organized, but what they are not is they're not alternating in terms of positive or negative charges. They're in these small little groups here. When it then dissolves, what will end up happening is, again, your water molecules are going to be breaking their attractions and trying to form new attractions with the iodine molecules, not ions, because they don't have anything to separate into positives and negatives. And the main difference is that what you're going to see is, again, a little later, you're going to notice that these are London forces. Again, an IMF, and that's the key thing here, right? When we are looking at ionic compounds, we're trying to break those ionic bonds, those electrostatic attractions. But when we're looking at molecular solutes, we're actually trying to separate some sort of intermolecular forces. So those are your London, they could be dipole, they could be the hydrogen bonding that you see here in water. When that happens then, we're going to be forming whatever attraction we can. Oops, that didn't come up. We're going to be forming some sort of attraction. And notice the difference, right? Our iodine, again, because it's a molecule, because it's I2, it's actually going to dissolve as that molecule. And so because it's dissolving as that molecule, we're going to be making these weak attractions. We don't have positives or negatives anymore within the iodine, and so it doesn't actually matter what portion of the water is being attracted to that iodine molecule. Again, we're going to see the iodine, we're going to see the water, and if we wrote this as a balanced equation, we would come over, and then as we look, In this case, we have water being the exact same thing here. So we're going to get rid of it because it's liquid on both sides and it's water on both sides. But then as we look at the iodine, we started out with a solid, so we want to keep that. And over here, we've now separated the solid molecules from each other and spread them throughout a solution. So we're going to indicate that by writing down that it's aqueous. That would not be a dissociation reaction, but it would be a dissolving reaction or a solution reaction. Right? And so we could watch it actually dissolve. Okay? When you take a look at your reasons for why things are going to in fact dissolve, what we're eventually going to see is that we really need to hit some sort of entropy. We need to be able to increase entropy. Now, if you don't remember what entropy is, that's the amount of chaos that can be created in a chemical reaction. So everything actually tends toward creating chaos. And so as long as we can get that chaotic nature, then we're definitely going to try to dissolve it. On the other hand, you also need that third step, that formation of the attractions between the water and our solute is really the biggest deal here. It's going to end up being a heat benefit where we're looking to see whether we have gained or released energy. And as we learn more about intermolecular forces, we're also going to be trying to create the best intermolecular forces. Whichever ones are stronger are the ones that you tend to then make. So that third step under the attractions, that's going to be a really, really big deal. Let me just go up and make one adjustment here. Breaking any sort of bond and or attraction is always an endothermic process. You need to be absorbing energy. As long as energy is absorbed, then you can actually separate two particles from each other. Forming then would be the opposite, which is exothermic, and that requires that you release some sort of energy. And so again, when we're looking at solubility and whether or not it can be soluble and dissolve or insoluble in a weak electrolyte, it's going to be this third step, that exothermic process, that's going to make the biggest difference. All right, last thing we want to cover is just your factors affecting the solubility also. And again, this idea here is really going into the nature of your solute and your solvent. What kind of attractions do they have? Are they ionic? Are they covalent? And then our temperature effects, we're looking specifically at two kinds of solutes, and that's solids versus gases. In a lot of the cases, an increase in temperature is going to be proportional, right? Proportional, that's the alpha symbol, to an increase in solubility. They'll actually dissolve better if you warm it up. Now, there are, of course, exceptions to that rule, but a good chunk of those solid solutes dissolving in a liquid solvent are going to have that effect where we can increase the solubility. And you might think of that as, if you want to dissolve some salt and you're trying to make pasta, if you warm the water, you see the salt is dissolving faster. Gases, if we increase the temperature, we will actually decrease the solubility. And you might have seen that if you sit down and you open a can of soda and leave it out. As the temperature gets warmer and warmer, the soda gets flatter and flatter. And that's because you're losing the gas solute, your carbon dioxide, that's trapped inside that soda. On the other hand, if we look at pressure, right, and again, solely looking at your gas and your solid solutes, pressure effects would mean that you're actually taking the container and somehow pressing down to help the dissolving process. When it comes to solid solutes, there is absolutely no effect. That is not going to help or hurt any sort of dissolving because the solid solute isn't going to have any sort of compressibility. The gases, though, as you increase the pressure, you definitely increase the solubility. And so when you take a look at, again, a can of soda, what you see is that the second that you release that pressure, all of a sudden the gases start coming out. So they clearly seal the cans to hold a bunch of extra pressure in there to keep that gas in it. And you can also see that there's actually some gadgets that they sell for like 2-liter bottles where the gadget will have like a little pump, and the goal is that you squeeze on the pump, and as you squeeze on the pump it adds extra gas in, and it's supposed to keep your soda from getting flat. And so, you know, whether you buy into that or not, it's kind of an interesting theory. So, all right, that's the end of our first lecture. So whenever you're ready, you can start on general reaction.